Solubility reactions are another important class of reactions that involve equilibrium. In this PowerPoint, we'll explore these types of equilibrium calculations, and in particular, we'll talk about equilibrium expressions and constants for dissolution processes. These are known as solubility products. And then we'll discuss how to use solubility products to determine molar solubility of an ionic compound in pure water and in solutions that already contain ions in common with the compound. This second situation involves the common ion effect, and this is an example of one of the ways that we can influence the solubility of a compound. Dissolving is an equilibrium process. When an ionic substance dissolves to its saturation limit, then it's in equilibrium with the reverse process, which is precipitation. So every time a set of ions breaks free from the surface of the solid, a set recombines in the solid crystal. And you have to be at the solubility limit for equilibrium to apply. If you have an unsaturated solution, you don't have an equilibrium situation. It's only when you have a saturated solution that you're considered in equilibrium between dissolving and precipitation. Let's consider the ionic compound silver chloride. So silver chloride is generally considered insoluble in water, but the truth is that just a small amount of silver chloride will actually dissolve. Its solubility is just extremely low. So that means that it reaches saturation level relatively quickly, and the equilibrium concentrations of the ions of silver and chloride, the dissociated ions, are just very small. But it is an equilibrium process, and we can write an equilibrium expression for it, and we can actually characterize those equilibrium concentrations of our ions using an equilibrium constant. So this is the balanced chemical equation for the dissolving of silver chloride. Solid silver chloride as your reactant, dissociating into the ions silver and chloride ion as your products. Now, if we were to write the equilibrium expression for this, notice that the only reactant we have is actually a pure solid, which is not included in the equilibrium expression. So the equilibrium expression ends up being just the product of the concentration of the ions that are produced during dissolving. So this is known as a solubility product, since it's simply a product of the ion concentrations, and it's characterized as a KSP value. A wide variety of solubility products can be found in reference tables, like this one. You'll notice that they're usually specified at a specific temperature. Rates are temperature dependent, so equilibrium constants are as well. And you'll also notice that you're not given the balanced equation for the dissolving process or the equilibrium expression. You're just given the formula for the compound and the equilibrium constant, the KSP value. Now, in order to use these constants, you do have to write both the dissolution equation and the equilibrium expression. The equations do always follow the same basic format. You have the solid reactant on the left, and the cation and anion that compound breaks apart into on the right as your products. So this is the same basic format that we used for the silver chloride reaction on the previous slide. And the equilibrium expression is just the product of the concentration of the ions raised to any coefficients they might have in the balanced dissolution equations. So in silver chloride, everything has one coefficient. So we end up with just the concentration of silver times the concentration of the chloride ion. If we were to break apart calcium fluoride, however, the subscript on the fluoride becomes a coefficient when the ions dissolve. So fluoride is a monoatomic ion, one element, one atom per ion. So my two fluorides in the formula become two separate fluoride ions when they dissolve. And this means that my solubility product expression is the concentration of calcium ion times the concentration of the fluoride ions squared. Now the next two substances contain polyatomic anions. And I recognize this grouping, CO3, as a polyatomic, more than one non-metal element. And I know that that's the grouping for carbonate. So there is actually a subscript on the oxygen in that polyatomic grouping. And it's important to note that for polyatomics, only subscripts that are outside of parentheses become coefficients on the dissolved ions. Those that are not outside of parentheses, like the 3 on that carbonate, are actually part of the polyatomic unit, and they stay as subscripts on the dissociated ion. So when calcium carbonate dissolves, it breaks apart into one calcium ion and one carbonate ion. And the equilibrium expression for this is just the concentration of calcium ion times the concentration of that carbonate ion. Now, for magnesium hydroxide, on the other hand, it does have a subscript outside of parentheses. So the polyatomic grouping is actually just the OH grouping. The 2 outside of parentheses tells me that I have 2 of that total polyatomic. So that actually becomes a coefficient on the ions when they're dissolved. So we end up with 1 magnesium ion and 2 hydroxides. And that solubility product expression is the concentration of the magnesium ion times the concentration of the hydroxide ion squared. One of the most common ways that we use solubility product values, or KSPs, is to calculate this molar solubility of a compound. So molar solubility is simply solubility, that saturation limit for that compound, calculated in units of moles of compound dissolved per liter of solution. And since we're simply calculating the saturation limit, we are dealing with an equilibrium concentration. That's what we want to find out. So this is an equilibrium calculation. And the first step for any equilibrium calculation is always to write the equation associated with it and the equilibrium expression. So we write the dissolution equation for calcium fluoride with the solid calcium fluoride on the left breaking apart into its 2 different types of ions, the cation and the anion, on the right. And that 2 subscript on our monoatomic fluoride ion becomes the coefficient on the right, and our solubility product expression becomes the calcium ion concentration times fluoride ions squared. Now, the second step is to create an ICE table and fill it in. So we start with dissolving this in pure water, so our initial concentrations of both ions is going to be 0. That means we're going to add in the change row, and we'll add in terms of X for the calcium ions and 2X for the fluoride ions, with the 2 simply coming from the coefficient on that fluoride in the balanced chemical equation. Our equilibrium row is simply the initial plus the change row combined, so it becomes X and 2X. Our last step is to substitute these equilibrium values of X into our expression and solve for X. X is the molar solubility. It is the moles per liter of our compound that will dissolve in water. So we substitute X and 2X into our equilibrium expression. We also substitute in the KSP value. X times 2X squared. The square applies to everything inside the parentheses, so that actually becomes 4X squared. multiplied by x, we get 4x cubed. We can then solve for x alone by dividing both sides by 4 and taking the cube root. And when we do so, we get a value for our molar solubility of 3.32 times 10 to the negative 4 moles per liter. Let's look at 2 more examples of this calculation. We'll do another molar solubility in pure water, this time for calcium carbonate, and then we'll calculate the molar solubility of the same substance in a solution that has a common ion. So what is the molar solubility of calcium carbonate in pure water at 25 degrees Celsius if the KSP value is 4.96 times 10 to the negative 9? So the first step again is to write that dissolution equation and the equilibrium expression. So we know that calcium carbonate breaks up into calcium ions and carbonate ions. That 3 stays attached to the oxygen since it's not outside parentheses. And we have in the balanced chemical equation 1 ion of each. So our solubility product is simply the concentration of calcium times the concentration of carbonate ion. We create an ICE table. Since we're dealing with pure water, our initial values for each ion are 0. It's 1 and 1 for the coefficients on our ions, so it's simply plus x and plus x for our change row. And our equilibrium x values are simply x and x. We substitute these into our equilibrium expression. It gives us x times x equals our KSP value, which is 4.96 times 10 to the negative 9. So we can isolate x, a single x by itself, by taking the square root of both sides. And we get a molar solubility value of 7.04 times 10 to the negative 5 moles per liter. So now let's look at how molar solubility of our calcium carbonate changes if we try to dissolve it in a solution that already contains 0.100 molar calcium chloride. So this is known as a common ion situation because the solution we're trying to dissolve our compound in actually contains an ion in common with the compound we're trying to dissolve. So the solution already has calcium ions and our compound also has calcium ions. In order to solve this problem, we're going to go through the exact same steps we did for water. We're going to write the dissolution equation and equilibrium expression first. And so we know for calcium carbonate it breaks up into 1 calcium and 1 carbonate ion. And there's our KSP expression for that. We're also going to create an ICE table. But notice that this time for our initial concentration, for calcium, we start off with 0.100 moles per liter. And this simply reflects the concentration of calcium in the solution that we're trying to dissolve in initially. So it's 0.100 molar calcium chloride, and it's a 1-to-1 relationship between calcium and calcium chloride. We have 0 for our initial concentration of carbonate ion, since that's not a common ion already in the solution. And to express our change in terms of x, we have to add to our products because we can't subtract from the carbonate column. So we have to add to the carbonate column. It's going to be plus x since it's got a coefficient of 1. And if we add to one of our products, we have to add to all of our products. So we also add to the calcium. And again, it's plus 1x for the coefficient of 1. We combine these initial and change rows in our equilibrium row. We get x for the concentration of the carbonate at equilibrium and 0.100 plus x for the calcium ion concentration. Now we make the x is small approximation because our KSP value is so small. So that will simplify our math if instead of 0.100 plus x, we can substitute 0.100 into our equilibrium expression. So we end up with 4.96 times 10 to the negative 9. Our KSP value equals 0.100 times x. We solve for x by dividing both sides by 0.100, and we get a molar solubility of our calcium carbonate compound in a calcium chloride solution of 4.96 times 10 to the negative 8 moles per liter. This is much smaller than what we got in pure water, which was 7 times 10 to the negative 5th moles per liter. So trying to dissolve your compound in a solution that has an ion in common already dissolved in it will limit the solubility of your compound even more. Before we move on, we should just check our assumption that saying x is small relative to our initial concentration was appropriate. So we divide our x value by the initial concentration of the calcium and multiply by 100. And as long as we are below 5%, then our assumption can be considered valid. And of course, 4.96 times 10 to the negative 8th divided by 0.1 times 100 gives you 4.96 times 10 to the negative 5th percent, much less than 5%. So our assumption is valid. So the last example depicts what we call the common ion effect. And when you try to dissolve a compound in a solution that already contains some of the dissolved cation or anion from another source, it will decrease the solubility of the compound. We can understand this from Le Chatelier's principle. Let's look at the solubility of calcium carbonate in hard water. So hard water is a term that's used to describe natural waters that have high dissolved metal content, like the metals calcium, magnesium, and iron. And we know that increasing the concentration of one of the products in an equilibrium reaction is considered a disturbance to the equilibrium. And according to Le Chatelier's principle, the equilibrium of the system will shift to minimize that disturbance. In this case, it shifts to the left, to consume the extra calcium ion. So the rate of the reverse process, precipitation, actually increases. It consumes the calcium and carbonate ion so that the equilibrium concentrations of these fall and our solubility decreases. So this is why we get a lot of deposits on bathroom surfaces and water pipes in areas that contain hard water. The metal ions in solution push the solubility equilibria of metal-containing carbonate and hydroxide compounds in the water to the left. So these compounds actually precipitate out of solution. And that's what we see in this picture. This is actually a water pipe from an area that contains hard water. And you can see all of those metal-containing carbonates and hydroxides coating the inside of the pipe until it's almost closed off completely. Another factor that can affect solubility of a compound is pH. It's particularly relevant to ionic compounds that contain cations and anions that are conjugate acids and bases. So take, for example, magnesium hydroxide. We know that the hydroxide ion is the conjugate base of the water molecule, and high concentrations are associated with basic solutions. If we try to dissolve magnesium hydroxide in a solution that's already basic, it will shift the solubility equilibrium to the left so that the solubility decreases. On the other hand, if we try to dissolve magnesium hydroxide in a solution that is acidic, we have a high concentration of hydronium ion. And hydronium ion reacts quickly and readily with any hydroxide dissolved from magnesium hydroxide. Essentially, it removes our product of aqueous hydroxide ion from solution. And according to Le Chatelier's principle, removing a product will shift equilibrium to the right to replace that product. And this means we can dissolve more magnesium hydroxide. In other words, our solubility increases. Another common reaction that can be paired with a dissolution process is the formation of a complex ion. So a complex ion is a central metal atom that's surrounded by ions or molecules. In this example, we have copper actually forming bonds with 6 ammonia molecules to form a complex ion. This is a very favorable reaction for copper, and it occurs readily whenever there is copper and ammonia together in solution. And we can see by the large equilibrium constant associated with this reaction that it favors the formation of the products. If we pair this very favorable reaction with a reaction that occurs sparingly, like the dissolution of copper hydroxide in water, shown here on top, we can essentially pull the less favorable reaction forward. And this is because the small amount of copper that's formed from the dissolution of copper hydroxide on its own is immediately consumed by reaction with ammonia in water to form that copper-ammonia complex ion. And this essentially removes the copper ion from solution as soon as it's formed. And we know from Le Chatelier's principle that removing a product from an equilibrium situation will result in shifting the equilibrium so that more product is formed. So it shifts the equilibrium to the right. In this case, dissolving more of the copper hydroxide. And if there's enough ammonia in the water to react with all of the copper ions, we can dissolve all of the copper hydroxide in solution. So we see this in the 3 pictures above. We've got 3 glass containers. On the right, we have pure water. In the middle, we've added some copper hydroxide, and just copper hydroxide. A small amount of that copper has dissolved, as indicated by the light blue color. Finally, in the container on the left, ammonia has been added to form that copper-ammonia complex ion, and all the copper hydroxide has dissolved, as indicated by that bright clear blue color. So pairing a process with a large equilibrium constant with one that has a small equilibrium constant can make that less favorable process shift forward to become more favorable. In summary, a saturated solution is at equilibrium with respect to dissolution and precipitation. Equilibrium constants for dissolution reactions are called solubility products, KSPs. And equilibrium concentrations of the dissolved ions are related to the molar solubility of the solute. And finally, you can influence molar solubility of a solute by the use of common ions in solution, which decrease solubility, or by pairing the dissolving equilibrium with a more favorable reaction that consumes one of the solute ions. This will increase solubility.